So the overarching goal of my research is to bridge in vitro and in vivo through the knowledge of mechanical biology. So how to say cell sense the world? It takes, right? It has been a central, main focus of the cell biology study for a long time. And in 21st century, people found out the other sense of a cell is touch. It also plays a very important role. It regulates cell function like growth, proliferation, or differentiation. So mechanobiology is to understand how this works. And in my lab, we are particularly interested in how to cell sense the dimensionality. Why I'm interested in this? Because cell in the animal body is naturally in 3D, but now practice are still on the package dish, so there's a huge gap. So 3D cell culture promise much better in good promise in cell therapy or drug screening. But 3D culture are very diverse. There's no standard, okay? And so that make it difficult to understand the role of dimensionality because the cell shape affects its function and it has a very diverse cell shape. So I took a very naive physicist approach, plastic chemistry into a sphere. So we turn this complicated matrix into a spherical pole. And I'm trying to show, so this will keep some key feature, but the essential part is that adhesion are distributed in 3D. And I'll show you mathematically, this is really a 3D culture because this, oh, I have to breathe. Okay. So this is the typical 2D cell culture of a fibroblast. And the green part is the focal adhesion. Red part is cytoskeleton, actin cytoskeleton. You see there's a very strong dorsal-ventral asymmetry, which is not physiological, okay? And just in our 3D pore, spherical pore, you can see the adhesion distribution is 3D. And you lose this dorsal-ventral asymmetry. The actin cytoskeleton are everywhere, just like collagen gel in the matrix. So our lab has a capability to culture a cell in a spherical microwell at a length scale of a cell. So at a length scale much smaller than 100 micron. And we found out that the actual cell, fibroblast cell, go through a cell cycle arrest. And this is fact is actually due to the curvature, not the confinement. Because we made the control of a cylindrical microwell, which is common practice in the microwell study because most of the microwell is fabricated through lithography, which is essential to be technique. Right? The cross section of the microwell will be identical, but our microwell is spherical. And then you can see when cells are in a cylindrical microwell, their proliferation is like flat because one of the curvature, the Gaussian curvature is 0. Okay? They still have a 0 curvature. Yeah, so our lab has a capability to make a ECM protein coated inside the microwell so we can isolate cell for a long time and observe it over time. Okay. And besides this, we also found out epithelial cells have very different behaviors from fibroblasts. They will adhere very well on the curved substrate, but in fibroblasts, they don't. They like to hang. Okay? And we can also control the ECM at different kind of distribution. Here, we decode it everywhere. We found out that at a negative curvature, cell height is smaller. And the positive curvature, the cell height is smaller. And we can also to construct a closed topology to make a cyst. Normally, a single cell of epithelial grows from a epithelial cell embedded in a matrix. They grow into a cyst. takes a week. And here we can just throw a lot of epithelial cells from a top-down approach to assemble a cyst. And we can also make them without any ECM coating, and they can grow like a domino. We can track how they grow over time. Yeah, so for this part, I want, because my cell biology is not so good, so I do some boring cell line. So if you are, I hope I can collaborate with a biologist that we can do more some exciting cellular system. Personally, I'm more pure physicist. I'm just curious about the mechanical behavior. Why morphology of epithelial cell, fibroblast on 2D. On 2D epithelial cell, it's a single cell. People always say it's always fibroblast. But on the curved substrate, they are very different. So intrinsically, cytoskeleton distributed has some different cross-linking something. Okay, so that's the first part of my talk. And the second part is very fresh out of oven. We just made it to the cover of Nature Physics of this month. Okay, so I collaborate with the Zhenghui Chen on the zebrafish. So we look at the wound healing process and the tail fin. So this is a nucleus of epithelial cell in the tail fin. We make a wound and they migrate, and you see this wave pattern. Okay, so Zhenghui 6 years ago, Zhenghui told me an amazing mystery about zebrafish. If you cut the tail, it will grow. And I didn't know that, okay? That's how little biology I know. And the mystery is that if you cut it different amount, naively you think the less you cut, the faster you heal, right? But it turned out no, they come back at the same time. So the question is, how do zebrafish know how much tissue it lost and grow at a higher, faster rate accordingly? And this is not unique to zebrafish. Actually, about 3 centuries ago, it has been reported on salamander, and also it has been reported on many other highly regenerative animals like starfish. So we started to look at this process because in the regeneration, there are 2 stages. The first stage is wound healing. The second stage is regrowth. And since the amputation happened in the first stage, any information here transmitted to the next stage. And to make the story short, I'll just tell you that we quantify the, since the migration has this wave pattern, and we can quantify this wave as the wave velocity and the wave traveling distance, and we change the parameter of changing how much we remove. We found out that the wave speed is independent of how much tissue we remove, how many, but then the more we remove the tail fin, the longer the wave travel, okay? And we made several experiments to show that all this wave transmission is through the mechanical coupling. And then we also construct a theoretical model to explain using just simple spring dash model to explain this wave behavior. And at the end, we show that the longer the wave travel, most of the cell growth proliferation happen within the where the wave travel, okay, because that part, the tail fin is stretched and there are more proliferation. Yeah. So this can explain why we remove more tail fin and then it will regrow back faster. Yeah. Yeah, so another, I'm just generally very curious about mechanical geometry of the cell. So I'm looking for geometrical pattern in vivo, such as a topological defect, which has been shown that control the Hydra's morphogen center or my lab, so I've been looking at the cell shape change from rigid to liquid. And I'll stop here and welcome for more question and collaboration.